And we continue. Very soon, on the main stage of AIJ 2023, you will see releases of the new and awesome innovations by Sber, GigaChat, OmniFusion, Kandinsky. I always look forward to announcing new models in video generation. I've already checked it out myself, and it looks very interesting. But first, you will hear about the multi-model modality architecture, AIRI OmniFusion. It processes text and images. Let's hear from the candidate of sciences, technical sciences, head of Fusion Brain AIRI, Andrey Kuznetsov, who will present OmniFusion. A big round of applause. Welcome on stage. Hello, everyone. So many people. Very happy to see you all. But let's not delve in theoretical discussions. Thanks to Maxime for giving such an apt gist. I would like to focus on the research area that we are studying at AIRI, jointly with Sber. And so the most peculiar thing is that when we think of language models, the first thing that comes to mind is, well, language. But many people, but not many people, think about applying this model to other domains, other areas, not just text, not just language, but other elements of architecture. So, first things first, text or multimodality. What are we going to focus on? Let's turn to the popularization of LLMs. We will see that text is indeed the basis of communication. And it is the basic modality that is used by humans in their interactions. Chatbots, of course, they are mimicking this mechanics, and they learn how to work with text because and so all the basic problems are in this textual dimension. But very often, and increasingly in messengers, we use more than text. We use audio, video, we use emojis and pictures, and we communicate this way through these modalities. And so we want to add these new modalities to our models as well, for them to be able to communicate more naturally with people. So we want more intelligent and naturally sounding models, assistants. The new architectural approach is based on these new modalities, and so the next logical question is, how do you add these new modalities to the language model? Basically, this is the task of training the model in new languages, languages of sound, image, video, and other modalities. This slide shows what it might look like, the LLM at the center and other types of data around it, adapted for its use, images, video, audio, graphs. On the left-hand side, we have the numerous inputs from different sources, and on the right-hand side is the different domains, different purposes that we can use it for. If we add, so then we get an M2 model, and if we add multilinguistic aspect, it is an M3 model. Since the 90s to 2010s, all the AI algorithms were mostly focused in statistical research, studying statistical patterns. And then we got our deep learning models, and presently we are speaking of the foundation models, pre-trained foundation models, which can tackle a lot of problems using different types of data. Let's see how it has been developing over the past few years, or the past year, rather. The increase in number of research papers on multimodal research since the end of 2022, so a bit less than a year has elapsed, and we already see this uptick from 1,800 mentions and references to almost 3,000 references. A significant growth, in my opinion. And the two key papers, central papers, published this year on GPT-4 vision and the description of the capabilities of GPT-4 vision is the dawn of LLMs with a big number of pages. I have to research using modalities of image and other modalities for healthcare problems and other problem solving. I will give you the examples. Anyway, the approach that is being used in multimodality architectures is more natural for people, which means it is easier to approximate the human brain. If we parallel the multimodality architecture to ourselves, sitting at the conference, we can be simultaneously sending text messages, picking at the slide and listening to the information that I'm relaying. So this is a symbiosis, a fusion of data from different sources. You are multitasking properly, you are not making errors in your text messages, and you are looking at the beautiful murals around you and listening to me, looking at the slides. Here on the left-hand side, we see the approach where the LLM is used as an orchestrator, which means we can connect a huge number of external systems in order to send queries to them and solve different problems. At the center, we have the end-to-end training where new modality is added to the LLM and it is trained in a uniform way, resource-intensive approach. And the third approach, which is gaining popularity and used in a lot of research, is where we sort of freeze the LLM and then we try to somehow train it to understand, through conversion, new types of data. And now the sexiest bit is the OmniFusion, our own architecture, which we developed this year, and I would like to tell you more about it. OmniFusion, at the base of it, it has an LLM, 7 billion. On the image, you see the adapters in red, which are transformer layers, which help you convert embeddings or property vectors into the space that is known to the language model. So the language model has this latent space, which it uses to describe the text it works with. And in order to convert the latent space of images, we are building special adapters which learn to perceive information from the images and convert it to language.
This means that our LM has the properties of understanding the images. It cannot describe it like an image caption, you know, but it is about the native perception of images. For visual encoder is the visual transformer. These are the two versions, and we made the experiments. Now, if you look at the details and on the content, the main sense is that the main idea is that we use special tokens in the input that are added for the training, and the data that are put into this inputted in this adapters are here on the lower part of the slide. Special input tokens, special tokens to divide bot and users, the tokens of questions and answers, special tokens to divide in data modalities. That is used for image start and end tokens. And the number of embeddings depend on which encoder we use, clip BG or clip L. This is the number where the number of embedders vary. Now, these are the adapters that help to convert data. At the same time, the training format means that we need instructive data, the sequential input data. This is a dialogue, the answer, the question, the answer, and the image, and so on. As for the training data sets, these are the data that we use for pre-training to level up the properties between the images and the text and by the latent space. And on the lower part of the slide, you see this data that we used during the fine-tuning stage, when we use instructive data so that it can have a dialogue with you, not just answer questions with pictures. And there are private data sets that we used. We haven't published that data set, but there are visual genome, GQA, and other data sets that are open source. Now, the training process was not that long, and if you look at similar research in this field, it confirms the fact that Formash GIL architectures are being trained in 1-2 GPUs, A6000, for example, that level. And in 2 days, you can have some good results and stable results. Now, as for the experiments, if you talk about the experiments, you need to understand and define the benchmarks. Since we work within the current research environment, and many teams are working to develop their own multi-model architectures, we have selected existing benchmarks. They're in English, and we started to train our model based on the current data sets. Now, these are the examples of the data sets. There are 8 of them. And these are the question and answer systems, in most cases. Now, these are the images from different areas. Now, there might be some single prompts for the images. Now, that's the real questions taken from blind people. And they have the question, describe a photo, and they try to imagine the image, the photo that is being described by the machine. And this is what is used with benchmark. There are data sets with Science QA. These are the data sets with various training lectures with schemes and diagrams. And this is to train the model to understand the scientific language. Now, as for the benchmarks, we have selected, as we think, the lava model. We looked at that model, which is the direct competitor. And comparing with this parameter, we built this diagram. On every point on the circle are the names of the benchmarks that we used for the training. Now, to measure the quality of the model and compare it with the benchmark, like in accuracy or perplexity, we put this metric to this radial diagram. And the metric selected for each data set is put in this circle. And it means that for each model, we can build this figure with several angles, several points, and the larger it is, the better it works with data points. Now, the 13 version is a little bit better than OmniFusion, but OmniFusion is going closer to the model Lava 13b. That means that the approaches to the training and building adapters, in Lava they use a linear adapter, and we have a transformer. And then the data collection and training approaches, sometimes you need to unfreeze the language model. So all the combination of these approaches in the research give you better results. And this 7-row version gives you quite a good result. Now, if you compare this model with various benchmarks that are highlighted here in the rows, you can see that the OmniFusion with a special SFT checkpoints give better results for the majority of the metrics if we take a pre-train for the basic model. That means that using the after-trained model is having an effect. That is very important. Now, we have developed our own visual benchmark. We use to assess the tasks of strong intelligence competition. There were text dialogues, text and image dialogues, audio modality, and other dialogues.
И мы померили на вот этом диалоговом.
And we have measured it based on our dialogue data set. These are the long dialogues, really. For every question, there were hundreds of answers. There was this pool of this conversation that was quite complicated. Based on this benchmark, our model was better than Lava B across all the metrics in the tasks put in this dialogue data sets. Now, obviously, we have compared different types of visual encoders. If you take a simple basic model for pre-train and fine-tune, then you can take an encoder that will be totally different. So we took two totally different encoders. And if you look at the quality of the results that we received, it's very important to understand what is the number of tokens that we received from every visual encoders. 576 tokens for image tokens, and for big G was 56. Now, clip bit large gives a better results for the metrics, and it's quite better. 56 vs 49. 68 against 66, 64 against 58. So actually, the results are better in some of the tasks, much better. Now we are kind of test driving the model with the experts. These are the examples shown by the basically, this is what the model is used for. You can calculate something, you can get some tags, generate some tags, and then it sees that these are the product glasses. It describes you what is the what animal it is. It recognizes the dish in the picture, and the this is the picture of Guangzhou and in China, and it actually understands that. Now there are there's an interesting example with the maps. It can also give you some information on where to go and what to sightsee in a city. If you talk about the number recognition, well, that is resolved on the level of data sets, because we use data sets for the numbers recognition. The number of cats, well, that's something that it can also understand very well. Now, this is a case. I'm not talking about GPT-4 vision, you know, like they show a broken finger and you can see that this is a broken finger, this is a fracture. There was a question about the wisdom teeth, where they should be removed, where they shouldn't be removed, and yes, it says that it should be removed here. And there are other images, and you should know them. There are faces. But actually, if you look closer, it is a picture. It's not a face. It's a picture made from various other pictures, various other objects. Like this Isaac Newton, could be Einstein. That would be difficult for me to understand. But anyway, a couple of links to dive deep in the models. It's in GitHub now. To dive into details, we don't have time to talk about that right now, obviously. There is a code of the inference in GitHub. The code point will also be published soon, so that you can play with the model. You can test drive it. Now that's my link to my Telegram channel, and the link to my channel, where I publish about the research papers published on different conferences about our progress, and I'll also try to make speeches on various conferences. AIRI, that's the research institute. and you can read all the materials there. It's a very exciting. These are very exciting resources, and you'll be able to select the area that you're interested in. Andrey, thank you. Andrey.